Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 3. Applications of the derivative. Section 4.7. Optimization problems.
Lesson 1. An introduction and a rectangular field example. In this section, we're going to be talking about what are referred to as optimization problems. And oftentimes in real life, we want to optimize a function by finding its biggest or its smallest output. For example, in business, we might want to choose a production level that maximizes our profit, or perhaps one that minimizes our cost. Or if we're in construction, we might want to maximize the strength of a beam, design it so that it's as strong as possible. Or perhaps we would want to minimize the amount of material that we need to construct a soda can, something like that. So those are the kinds of problems that we encounter in this section called optimization problems. Now, the problems that we actually do in this section may seem slightly contrived to you, and they are. They're simple problems, but remember, just like the related rates problems that we did earlier, these are your initial introduction to real-life problems that you might actually encounter. So let's go ahead and look at a specific example. A rectangular field is to be bounded by a fence on 3 sides. Down here I have a picture. The fencing is this stuff in purple, so we only use fencing on 3 sides, and by a stream on the 4th side. So the stream makes up the 4th side and we don't need fencing along this 4th side. Assume that this stream is straight. It looks a little bit curved in my picture. That was just to give you the idea that it was a stream. Okay. Find the dimensions of the field which maximize the area. So we want the largest possible green area that we can get if 1,000 feet of fencing is available. So you look in your warehouse, you only have 1,000 feet of fencing to make this field. All right, let's see if we can go ahead and break this problem down into steps. All of the steps that we use will be used for each of the optimization problems that we encounter. But just like with the related rates problems, each optimization problem is slightly different and presents its own challenges. But the same steps will help us to attack and pull apart the problem into manageable parts. So let's go ahead and see if we can think about this first step. The first thing we'll do is draw a picture. Well, in this case, the picture is already drawn for us. But let's go ahead and name the quantities that vary. So anything that varies, we're going to use a variable for. And we'll also label anything that's constant. So if there's a dimension that's constant in the picture, we'll label it that way. Okay, so in this case, I'm supposed to build a rectangular field, but my dimensions could be different. I could have a really kind of square field, I could have a long skinny field, so this dimension and this dimension could be different. And so I'm going to label those with variables. This dimension maybe I'll call X, and this dimension I will call Y. And I want to use variables for those specifically because these dimensions are the ones that can change. There really aren't any dimensions that are constant in this case. They don't tell me that the width has to be 20 feet or something like that. So there are no constants that I'm going to add into this picture. So that is step 1, is just to draw the picture if it isn't already provided, and then name all the quantities that vary with variables, and anything that's a constant, just label it with that constant. Okay, I put a little red star by step 2. This is a very important step, and what we are going to do is to try to identify the function. What function am I asked to maximize or minimize in the problem? And it will always specify whether it wants me to maximize some function or whether it wants me to minimize some function. So we want to identify the function we're supposed to maximize or the function we're supposed to minimize. And I put a star by this because this is the main function that we're going to be working with throughout the problem that we're going to be focusing on. So I'd like you to go back up to the problem and read through it and see if you can tell me what it is I'm trying to maximize or perhaps minimize. When I go back up to the problem, I notice it says, find the dimensions of the field which maximize the area. In other words, maximize this green area of the field. That is my main goal in this problem, is to figure out what the dimensions x and y should be that make the area, the green shaded area, as big as possible. So the function I'm trying to maximize is the area of the field. And I'm just going to put in parentheses that I want to maximize that rather than trying to minimize it. So in this case, I'm asked to maximize the area. Let's go ahead and see if we can write down what the area is in terms of the dimensions that we put into our picture in step 1. The area of this field, well, it's a rectangle that's x feet by y feet, and area of a rectangle is just the width times the length. So the area in terms of what I've labeled would be x times y. That's the function I want to find the maximum of. But there's something rather unfortunate about this particular function. Notice that a is not just like a function of x, like, I don't know, x cubed minus 7x plus 5. It's a function of x and y. So a is a function of 2 variables, and that is a problem. Why is it a problem? Well, I've only learned to find the maximum or the minimum of a function of 1 variable. If it were a function of just x, I know how to find the maximum. I find the derivative and then I analyze the critical numbers that I get and decide, is it a maximum, is it a minimum? But if it's a function of 2 variables, I have no way to find the derivative. I don't know how to maximize a function of 2 variables. So somehow we must rewrite our function as a function of 1 variable. It's the only way I know how to find the maximum of a function is if it's a function of just x or a function of just y. To help me figure out how to write this as a function of 1 variable, I'm going to use what's referred to as the constraint equation. It's called that because it reflects the constraints in our problem. When I want to maximize the area of this field and I say, what should x and y be? Can they be just as large as I want? Can I make x 100,000 feet and y 200,000 feet and have an enormous area? Well, no. There's something in the problem that is constraining us. So let's see if we can decide what constrains our situation. Why can't I make x and y as large as I want to? Well, pause the tape for a moment and see if you can see what it is that's constraining the maximum size that x and y could be. Okay, let's try to answer this question together. Notice that it says, find the dimensions of the field which maximize the area if, and here comes the constraint, 1,000 feet of fencing is available. In other words, we have 1,000 feet of fencing to use on these 3 sides. By the way, what's the length of this side? If this side's x, this side must also be x. So we have 1,000 feet of fencing to use on this side, which has length x, this side, which has length y, and this side, which again has length x. So that's what's constraining the situation, is that there are 1,000 feet, I'll say only 1,000 feet of fencing to use on those 3 sides. I'll say for the 3 sides. So we can't just make x and y enormously long because we only get 1,000 feet to wrap around those 3 sides. Well, how would I write that as an equation? Pause the video again and see if you can write down an equation that expresses the fact that we only get to use 1,000 feet for this side, and this side. Okay, let's try this together. I get 1,000 feet for those three sides. So 1,000 feet for this side, which is x, and then I'd add on the length of this side, this is y feet, and then I'd add on the length of this side, which is another x feet. So I have 1,000 feet of fencing that has to be divvied up between these three sides, the x, the y, and the other x. Or you could write this as 1,000 is equal to 2x plus y. And this is what's referred to as the constraint equation. So now let's go ahead and look at step 4. It says, solve the constraint equation for one variable in terms of the other. And here's my constraint equation, 1,000 equals 2x plus y. What would be easiest to solve for? I suppose I could solve for x, but it would involve dividing by 2. Y looks slightly easier to isolate, so I'll solve for y. Y would be 1,000 minus 2x. And now notice that I have y written purely in terms of x. How can I use that to rewrite a equals xy as a function of just one variable instead of a function of two variables? Well, I could take this and substitute it in place of my y. So y is the same thing as 1,000 minus 2x. That means I can replace this y with 1,000 minus 2x. So let's do that. I have a is equal to x, and in place of y, I'm going to put down what the constraint equation said it was in terms of x. It's 1,000 minus 2x. And notice that now I've written a purely in terms of x. It's a function of one variable instead of this troublesome function of two variables. I could even multiply it out if I want to. A would be 1,000x minus 2x squared. And sometimes we even write, instead of a here, we'll write a of x, because it's now a function just of x. Well, let's go to the next page and see what step 5 is. Okay, so let's go to the next page where it asks us, what's the range of possible x values? Remember that when we're thinking about this rectangle next to the stream, here was x, and here was y, that these are dimensions of a rectangle. X is the width and y is the length. So they can't be a negative value. So notice first of all that x has to be something that's greater than or equal to 0, and y has to be something that's greater than or equal to 0. So when we're thinking about what's maybe the largest and smallest possible values for x, x has to be something that is greater than or equal to 0. But I'd also like to think, well, what's the biggest value x could have? And if you think about the constraint equation, remember that was 1,000 equals 2x plus y. X will be its largest when y is its smallest. So if we made y very, very small, think of y shrinking down and having a length of this rectangle just equal to 0 feet. I want to say, well, I have an x on this side and an x on this side. I'm using 1,000 feet for those two sides, and I'm not going to use any feet at all on the y side. It's like this rectangle has degenerated into just a little bitty line segment. So if I used 1,000 feet on these two sides labeled x and didn't use any of it on the y, you notice that half of the 1,000 would be here, so x would end up being equal to 500 feet, and the other half of the 1,000 feet would be used here, and this side would also be 500 feet of fencing, and no fencing is used down here at all. You can also see that from the constraint equation. If I make y its smallest, and the smallest y can be is 0, I will be able to figure out what the largest value x could possibly be is. And I just replace y with its smallest value and solve this for x. You notice if I divide both sides by 2, I get x equal to 500. So I can find this maximum value of x by making y its smallest, namely 0, and then just solving in the constraint equation for x. So the biggest that x can be is 500 feet. So when we talk about the range of possible x values, we're just saying, oh, what's the smallest x can be? In our physical problem, the smallest x can be is 0. And what's the largest x can be? Well, in our physical problem, x is its largest when y is its smallest. And when you plug that in, we get x equals 500. Or you can just think about the picture as we did here. Okay, let's look at step 5. It asks us to find the absolute maximum. It says or minimum, that's in general, but we are asked to find the maximum of our function. And remember that the function we're trying to maximize is the area of this rectangle. We already wrote it purely as a function of x. It's 1000x minus 2x squared. But we now also have this range of x values. X has to be something in the interval from 0 to 500. We really want the biggest possible output, so we want the absolute maximum of this function on this interval. Notice this is a closed interval, and we have a method. If we have a continuous function, it is continuous. I should mark that down. A of x is continuous because it's a polynomial. Put that in parentheses. It's a polynomial. So it's continuous everywhere. So in particular, it's continuous on this closed interval. When we have a function that's continuous on a closed interval, we have an easy way to find the absolute max and min. Let's see if we can remember those steps for how we go through finding the absolute max and min of a continuous function on a closed interval. Remember, the first thing we do is we find the critical numbers. So I'll find the critical numbers for a of x. How do I find the critical numbers? I have to find the derivative. Well, a prime of x, just taking the derivative of this, would be 1000 minus derivative of 2x squared would be 4x. Let me go ahead and factor that. It looks like there's a common factor of 4 that I could pull out. And so I'd get 4 times 250 minus x. And let's go ahead and see this derivative will be 0 when x is equal to 250, and the derivative will never be undefined. So I just get one critical value at x equal 250. That's a place where the derivative is equal to 0. I'll just put that in parentheses, and I'll put in parentheses a prime is never undefined. Prime never undefined. So we only get one critical number, x equals 250. If you put the units on it, it's 250 feet. Well, there are two ways to determine whether this is an absolute maximum, or maybe it's an absolute minimum, or maybe it's neither of those. But let's use the quick way that works when we have a continuous function on a closed interval. And remember from an earlier section, you learned that really all you have to do is take this critical number and throw it into the original function, throw it into a of x, as long as you also check the endpoint values. So this is the critical number value. We will also check a at the two endpoints of our interval. And what is our interval? It's from 0 to 500, so I'd have to check a of 0, the output value at that endpoint, and the output value of a of x when I plug in the other endpoint, 500. So we just check the value of the original function a at 250, at 0, and at 500, and whatever number over here comes up the largest, that is our absolute maximum area. That's one of the wonderful things about having a continuous function on a closed interval and looking for the absolute max in that situation. So I'm going to plug 250 in. I go back to my function a of x. It would be 1000 times 250 minus 2 times 250 squared. And that comes out to be, I'm cheating and looking at my notes, 125,000 1,000 would really be in units of square feet because it's the units of area. If I plug 0 into a of x, I would have 1,000 times 0 minus 2 times 0 squared. I would end up getting 0 square feet. Well, that's not going to be the maximum. That would be if you shrunk x all the way to be 0, and you'd have a rectangle that's 0 feet wide by 1,000 feet long. That's going to have an area of 0. Definitely not the maximum area. And then I could check a of 500. Well, if I plug 500 into this, I get 1,000 times 500 minus 2 times 500 squared, and that also comes out to be equal to 0. So these two are definitely not the absolute maximum of this function on this closed interval. In fact, they are the absolute minimum output. They're the minimum possible area. And what I have right here must correspond to the absolute maximum area. And notice that absolute maximum area occurred at x equals 250. So I actually know now what the width of my rectangle should be to get the maximum area. X has to be 250, and since it's a length, we have to use units of length. It would be 250 feet. My picture is starting to come together here. What I'm saying is that I use x equal 250 for this side, and I use x equal 250 for this side. I really want to be sure that I found all the quantities asked for in the problem, and you might remember, if we go back to the original words of the problem, that it said find the dimensions of the field with maximum area. And remember, by dimensions, they mean just find the width and the length of the field that give you the maximum area. So when they say dimensions, I've already found one of them. It's what I'm thinking of as the width. But now I still have to wonder, well, what's the corresponding length of that rectangle? And so we have to think, well, if I know what x is, how do I find what y is equal to? And to find what y is equal to, you can either think about the fact that you have 1,000 feet of fencing for these three sides and just subtract in your head, or you can just return to the constraint equation, and that's what I'm going to do, but either way is okay. Remember our constraint equation, and I usually like to go back to the constraint equation to the point where we solved for y in terms of x. Let me put the other page back up for a moment. Remember, we said 1,000 equals 2x plus y, but here we solve for y in terms of x. So I've already done the work of isolating y, so y is 1,000 minus 2x. Let me write that down on this last step. Y is equal to 1,000 minus 2x. That's just the easiest place to plug in. So all I'm going to do is plug in the value of x that we found that maximizes the area. So I replace x with 250 and find the corresponding y value. So what would I get? I'd get 1,000 minus 500 would be 500, and the units on that would be feet again. Since y is the length of a rectangle, it has units of length, which is feet. So y turns out to be 500. Of course, you could also get that just in your head, saying, well, if I use 250 here for x and another 250 feet here, and I only have 1,000 feet of fencing total, I've already used 500 on these two sides, I would have 500 left for the y side. So you can also do it that way. And then the area of this rectangle, this maximum rectangle, would be 125,000. It would really be in units of square feet. And that's what you would get if you multiply x equal 250 by y equal 500 feet. You'll get 125,000 square feet. That was not actually asked for. They didn't say how big is that maximum area. They wanted the dimensions of our rectangle. At the end, when they ask for the dimensions, we usually write it the way you write, say, the dimensions of a carpet or something like that. We'd say, oh, it's 250 feet by 500 feet. So those are the dimensions of the rectangle that gives you the largest possible area. Okay, well let's go ahead and look at our second example.